on fusion as an energy industry. And what we're going to talk through here is really helping you understand how we look at fusion differently when we're just focusing on the core science and trying to achieve this massive scientific breakthrough in multiple domains, and how we think of it when we actually need to turn that into a cost-competitive energy industry that produces hundreds of gigawatts, maybe terawatts on the global power grid. So it's a really different type of question, and we're really excited about understanding how to answer that question, because it really is where a vastly larger number of people can become involved in helping fusion become a really valuable part of our energy grid. So I do have the chat open. If people have any questions, please jump in at any time and just drop a message in the chat. I'll also give some time for questions at the end. So like we mentioned, there are many different types of fusion. And I think this is really critical to understand that there are so many different approaches, and each of them is targeting different combinations of scientific and economic challenges around the viability of fusion, including some of the topics that you guys have already started asking questions about. So while even this is just a snapshot of hundreds of different designs and approaches that are out there in the market, I wanted to dive in a little deeper on a few specific designs to give you a bit more of a taste of what these look like and what problems people are solving for. So I'm going to give you one example of each of 5 different major designs that are being approached in the industry right now. And you'll see, what the design is, the fuel type being used, as well as some other examples of companies that are pursuing this type of approach. And I'll give you a bit of a high level of why they're pursuing that approach as well. So first of all, we have the tokamak approach. So this is the kind of donut design you can imagine with plasmas moving around inside that donut. And this was really a design that was created around conquering the core challenge of the fact that magnetic fields, they continue around and reconnect, and we want them to be all concentrated towards moving, guiding, and controlling that plasma. So by connecting the two ends of a solenoid, effectively, we're wrapping that magnetic field around and making it more continuous. Commonwealth is an extremely well-funded company in this space. They now have over 1,000 employees, and they're moving the industry forward very rapidly. However, one of the challenges with the tokamak design is that it is a pulsed design. So if we want to get into the details of that, we can. But for those of you who are a little more on the scientific side, essentially, the current is driven by the ramping of a central solenoid. Ramping of any energy cannot be infinite, which means that we have to cycle these pulses of ramping. What a stellarator design does, like the one designed by Type 1 Energy, as well as these other fusion companies, is it allows for a more continuous production of fusion power without that pulsing effect. So that increases something we're going to talk about in a sec, which is called the capacity factor, and basically talks about how much of the time after you've built this machine is it actively producing power, and how much power is it producing per minute, hour, week, however you want to look at it. Then we look at other designs like field reverse configuration produced by companies like Helion, TAE, and more that are tackling this from a whole other angle, which is looking at when you have to build a machine that's large, it consumes a lot of materials, and it has to be designed in ways that are much more site specific, and require a lot more fabrication. Whereas when you can build a smaller design, it's more able to be produced in factories, produced in higher quantities. And as we'll learn later in the techno-economics section, this is a big factor in what drives reduction of cost. So Helion is using a different type of fuel, DH3 that we talked about, and also a field reverse configuration, which to give you the best kind of visual of this, you can imagine an hourglass being held sideways and a donut of plasma being generated in each end of the hourglass. by spinning those plasma and then shooting them down this, you could say, the stem or the funnel of the hourglass, so that they smash into each other right at the most compressed point of that hourglass. It creates density through the compression. It creates more density through the impact of the two together. And this, similar to what we were talking about with the inertial confinement fusion, allows them to benefit from that extremely high density to not require as much duration in in achieving their Q. Then we look at other approaches still. So, more alternative approaches like magnetized target fusion, with a company called General Fusion out of Canada and others like Zap Energy, where they're really trying to optimize what is the minimum cost to produce each type of force that can contribute to that triple product that we're talking about. So they've been innovating on areas like creating a blanket that's liquid. A blanket that's liquid. We'll talk about the blanket later, but essentially, it's how we capture the energy and turn that into electricity. It's also, but they're also using a mechanical system to create density rather than having to generate that through the plasma or through magnets. So magnets have reduced impact as the distance gets greater, but if you use something like pneumatic power, which they're using with giant pneumatic ramrods here to compress the physical space that this plasma is existing in, they have a more cost-efficient way of generating that density. And then finally, we have inertial fusion, the other major approach being pursued by companies like Pacific Fusion, Marvel, et cetera. And this is what we talked about before, where essentially multiple lasers or other particle beams are being channeled into a central target. Sorry, did we have a question? I heard a voice.
Actually, some of you are dialing in at like.
Sorry, can everyone just mute themselves, please?
10:30 p.m. in Delhi.
All right. Thank you. Okay, so as I was mentioning, you have lasers or particle beams being targeted at a central target that then implodes to create a very momentary but extremely high density pulse of fusion. Before I continue, there are multiple different types of fuel type though, so I wanted to recap on that. We talked about a few of these different designs. But again, beyond deuterium, tritium, there's deuterium, helium, proton boron, and then the three major categories, magnetic, inertial, and magneto-inertial. You can see kind of how these different players are distributed. And then separately, one thing that's really interesting is looking at where these companies are operating within the world and how they're distributed globally. So the big trends that you'll see is the US is a major center of fusion, but other players are also distributed across Europe, and China is also driving forward very rapidly. Now, what I'm showing you now is just the companies working on fusion machines that will actually generate plasma or generate a fusion reaction to put power on the grid. Whereas if we were to look at the entire fusion industry, far more countries are involved in other areas like component production all the way through to raw mineral mining and extraction. I'm just hearing somebody come off mic. If you can put yourself back on mute, that would be great for everyone's sound quality. So the next part that we're going to talk about is really how should we think about the energy production capabilities of fusion as compared to other energy sources. So looking at this table from the Arthur D. Little report, we can see how fusion compares to other sources like storage, hydropower, solar, coal, etc. Really in its application for different uses. So as baseload power, fusion has that ability to produce continuous, ongoing power, where solar, for example, may be inconsistent and really depends on when there's light and not clouds available at the same time. Looking at other things like land usage, fusion is extremely power dense in terms of the amount of energy we could theoretically create within a small physical space, and other areas like greenhouse gas emissions. But when we look at the different applications of where fusion can actually be used and what industries it's relevant for, it's also important for us to break down each of the different kind of underlying reasons why fusion might or might not be appropriate for each use. So I'm going to walk you through now several of the different key factors that are unique about fusion and that make it a special case. Somebody just shared their screen. If you can stop sharing that, I'm going to pull mine back. I don't know if that was by accident. Okay, I think we're back on my screen. So fusion as an energy industry. First of all, let's look at this claim that fusion power or fusion fuel is infinite. So you may have heard this claim before. And essentially, it's related to the fact that some fusion designs are planning to use deuterium as a primary fuel. Like we mentioned earlier, Jack was talking about, this fuel is available in seawater, and it's in such an enormous abundance that we could theoretically power fusion machines forever with it. But the story is a little more complicated than that. So I really want you to understand the true constraints that we need to plan for and not take it as a given that fusion will have infinite power forever. I guess that's redundant. So first we talk about power density, and this is the main reason why people talk about fusion having infinite availability of power. So you can look at things like sugar, coal, fat, gasoline, and then there's uranium. So uranium as a source of energy has a power density many orders of magnitude higher than other fuel sources we use, such as crude oil, coal, etc. And uranium is what we use for nuclear fission. But then when we look at deuterium tritium, the mix used for fusion, it's even a significant amount more power dense than uranium. And the same amount of fuel would actually have 4 times the amount of energy that can be released from it through a deuterium tritium fusion reaction. So that's already exciting because it means that even a small amount of fuel could actually provide an enormous amount of power compared to really any other active form of energy. But what's crazy about that, and really even mind-blowing to think about, is that when we look at the amount of fuel that's actually available, it's enormously higher in raw volume as well. So there are predictions that all uranium on Earth could be consumed by as early as 2080, with other predictions going out as far as 100,000 years from today. When we look at deuterium as a fuel source, even if all humans on Earth were to consume as much energy per person as the most modernized and energy-consuming countries today, we would have enough deuterium to power the entire world for about 8 billion years. This is critical to understand that for context, because it's such a massive number, we expect the sun to die entirely in 5 billion years. The entire history of the Earth, the existence of the Earth, is about 5 billion years long. So we couldn't even use this much power in the entire conceivable future of the Earth. So that's great news. But here's where there's a little more complexity to the story, and where it's really important to understand that there's nothing, given or automatically handed to you with fusion, and that is the rest of the fuel cycle. So first of all, like we mentioned earlier, there's not an infinite amount of tritium. You can see on the bottom, there's a graph of our global tritium supplies. Essentially, there's approximately 25 to 30 kilograms in the entire world of available tritium. And that tritium is produced by a type of nuclear fission reactor called a CANDU reactor, but it also has a half-life. So even as that as that tritium is being produced, it's dying out, and its viability is diminishing over time. What's more is that CANDU reactors are being increasingly phased out or retired, so this production will not be going on forever. What's more is that even beyond tritium, which we do plan to generate by actually creating it as part of the fuel cycle process and as a product of the burning plasma, the only way we can do that, and we'll go through this more in detail later as well, is by using lithium as a breeding agent, as well as beryllium, in order to create a reaction that produces more tritium. And both of those are materials that we should be concerned about as well. So when we go into this in the supply chain section, I'm going to walk you through this in detail. But I wanted to give you a taste of where some of this complexity comes in. Again, a note, I'm talking about deuterium, tritium here, and each different fuel cycle will have its own constraints and capacity. So again, we talked about that there are different types of fuel that can be used. And we had a question as well about what are some of the constraints about those type of fuels. We got a great answer from Jack, so I'll jump down here to boron. Actually, boron is not a fuel which we see as being highly constrained. So there are potentially viable reasons to believe that this could be a credible fuel source for fusion. And that's probably one of the reasons why it's one of the more pursued approaches. Rather than, for example, deuterium, and others. So, like I mentioned, there's not just fuel. There's an entire array of different factors that really drive how we see and understand fusion as a way of producing electricity when we start thinking of the larger, Q economic, or at least Q engineering. And one of the most critical factors there is what's called capacity factor. So two things really drive the capacity factor. One is going to be the percentage of an ongoing kind of operating day, you can imagine, in which the plant is generating power. So this could be things like whether it's a pulsed or continuous reaction. But there can be other design components that go into that as well. The other part, and one of the major drivers of capacity factor, is really about how long it takes to maintain the system and how often you have to go in and shut down the system to do that maintenance. So in a traditional nuclear fission power plant, you can sometimes have expected maintenance cycles that can take as long as a year to do the regular repair and maintenance. And that drives a significant majority of the total time during a nuclear fission power plant's life that it's not actually putting electricity onto the grid. For fusion, because this is a critical factor, it's important to understand that for fusion, current estimates are putting it slightly lower than fission at about 85%. However, there are lots of factors that can go into pushing this to a higher number. And even such small changes, we've seen examples from the fission industry, even such small changes as switching to different components outside of that core generation. So we talked about helium. Helion's trying to avoid several of the large components which often break down by actually creating a ring around their design, and that actually stretches out during the pulse of a plasma reaction. And this movement, again, this is a big oversimplification, so apologies to the scientists in the room, but essentially they're trying to create induced current without actually converting heat to steam through a turbine to electricity. And by doing that, they're simplifying the system in a way there's much less maintenance that needs to be done. So there's lots that can be brought in this space. Next, we talk a lot about the safety and the cleanliness of fusion energy. And I think what goes missed is actually not so much about how safe fusion is, but by contrast, how incredibly dangerous and polluting some of the other energy sources we just take for granted really are. So when we look at coal, 24.6 deaths per 150,000 people worth of energy consumption coming from coal are being created. Even when you by contrast, even when you factor in major disasters like Chernobyl or Fukushima, the equivalent number for nuclear energy, that's traditional nuclear fission, is 0.03 deaths, and then 6 tons of total carbon emissions. When we compare to that, where fusion would sit on this graph, it's even lower. The amount of deaths would be almost unmeasurable, because that 0.03 includes deaths that are the result of nuclear meltdowns. And what I'm going to show you in a minute is fusion is actually functionally not capable of that type of problem, and which we consider, I think, as a society to be the biggest risk and the biggest fear around nuclear energy. So Sergey walked you through how there's two different types of reactions that we have for fission and for fusion, respectively. In fission, we have what's called a chain reaction, where you can see the initial particle that triggers the first reaction that goes into the system and breaks apart that large atom actually releases multiple smaller atoms, but also the exact same particle type, which can go on and trigger further reactions. So we call this a chain reaction, but importantly, it's a growing reaction because we split the atom apart and that triggers more and more and more reactions to happen, which means we have to actively control that reaction so it doesn't grow too fast or too large. But anytime it's not being controlled, it will grow out of hand and out of control. Fusion, on the other hand, we're actually bringing those atoms together to make larger atoms. So partly because of this, and partly because the neutron that comes out of a fusion reaction is not either of the inputs that goes into a fusion reaction, it does not trigger a further sequential reaction in the way that the neutron coming in is the same as the neutrons coming out of a fission reaction, triggering those further reactions. Most critically, though, the amount of total fuel available in a system is just orders of magnitude different. We can see that in fission, we're carrying sometimes up to 75 tons of uranium fuel, whereas in fusion, we're talking about a few grams actively in the system creating plasma at a time. And what all of this means is that if there's any failure, any break, any stoppage of energy that happens within a fusion system, that plasma reaction instantly collapses. And even if we were to open up the walls, which is very impossible with a fusion reactor, but even if you were to crack it open and expose all of that to the internal environment of the plant, the amount of active plasma is so small in terms of the number of actual atoms that its impact would be extremely small and low in danger compared to fission as well. This is a point where we've had a few questions in the past, so if you do have any questions, again, feel free to jump into the chat and I'm happy to pause. The next part that we have to think about as we look through the life cycle of fusion and what drives the total cost and its viability as an energy source is not just how we create the energy and what the electricity sources are, or the offputs and waste that it creates during its life, but also how do we manage the waste at the end of life of a fusion reactor. So the reason I'm asking that question is that when we look at the different fuel types for fusion, I won't go into every detail of this chart, but essentially the big message is that the fusion fuel itself is not generating as much radioactive waste by a massive order of magnitude as fusion reactors. But what it does do is that those reactions actually charge the containment unit and the structural materials that we build fusion machines out of, so that at the end of life, we have to very carefully manage the waste that comes from disassembling the machine itself. Even here, though, as long as we make the right choices, there's an enormous opportunity for fusion to be orders of magnitude safer than fission or other comparable players in the market, even including coal. So what you can see up here is that the lifespan of kind of at-risk waste from a fission reactor that needs to be carefully managed is in the tens of thousands to potentially hundreds of thousands or even millions of years. And these are timescales that are almost inconceivable. When you look at the different curves for fusion, you can see they drop off much more dramatically to nearer to safe levels. But what's important is that there's a critical difference that's driven by what different types of materials we use to design these reactors themselves. So I've just chosen two examples here, reduced activation ferritic steel You might have heard RAFM steels as well, or vanadium alloys. And even between these two, you can see that there's a very important breaking line that they cross depending on which one we use. With reduced activation ferritic steels, even though the risk level, the emission level drops off dramatically within a short period of time, it's still above the level of coal, which we consider to be disposable without nuclear safeguards. And it's also doing that over a period of 100 years, which is still within the timescale of a society or of a company, but not necessarily within the timescale of a single person's career length. And the reason this really matters when we look at vanadium alloys dropping off within that period down to a level below or within coal is that the reason we're concerned about waste from fission plants, where we're maybe not as concerned about our ability to manage the waste from chemical plants or other types of toxic waste, is because that lifespan, being multiple generations, longer than societies exist, longer than human cultures exist, means that we cannot be certain in any credible way that we will have an ability to maintain a containment or protective structure around that waste over that period of tens, thousands, or millions of years. Whereas if we can keep this within the 10, 15, 20-year time frame, this is a length of period where we can be absolutely sure that it's realistic to have continuity in that management protocol, because it's within the length of even a single person's career, let alone a management structure within an organization. So this is a really important differentiator there. As you can see as well, like we talked about in the last slide, the actual ongoing waste from the fuel is already down at a coal level. So it's not something that we need to manage in an exceedingly high containment type of way. Come back here. So now that we look at kind of the fueling, the startup, the conclusion, and dismantling of the plant, we need to think about the timeline that that's operating over. So when we look at energy technologies, we talk about a metric called LCOE, or lifetime levelized cost of energy. And that levelized cost of energy is driven partly by the upfront cost, partly by the operating cost, but also by the factors that we talked about earlier, like our capacity factor, and potentially most importantly, by the life length of the plant. Because with especially electrical technologies or non-emitting technologies, a lot more of the investment is upfront, and we have to defray that over a longer lifespan of the plant. What we can see here is really encouraging when it comes to fusion power, because we're expecting lifespans well within the range of other competing power sources, such as nuclear and coal. And this is, and so where does that land us in terms of the cost? We talked about the LCOE. So first of all, I want to call out what we're going to talk about here. The specific numbers are based on modeling referring to deuterium, tritium, magnetic confinement fusion. There are many different designs, and many of those designs are specifically targeted at reducing the cost of producing fusion energy. However, we are currently seeing that there's a potential for the cost to be very competitive and in line with other players, or for that cost to be exorbitant. And what's important to take away from this slide is that the biggest portion of this high-end cost is actually coming from the regulatory environment. So it's not even the construction cost, it's not the materials, it's not the energy to actually power the systems of the plant. It's the fact that some countries are currently looking at regulating fusion as if it were fission. And like we learned earlier, the safety constraints, the waste production, et cetera, just don't justify that level of regulatory burden. And yet it's one of the largest drivers of cost in the entire nuclear fission industry. So we'll talk about policy a little bit later, but this is a place where we have an enormous opportunity to make a fusion extremely cost competitive within the market. One other important factor to consider here is that the willingness to pay and the green premium for fuel that's not combined cycle gas or that's not coal-based is actually quite significant. Even residentially, people are willing to pay another $15 per megawatt hour. And commercially, they're willing to pay 2 to 3 times versus retail rates if they can be assured that their energy is coming from a green source. So by now, hopefully you're all very excited about some of the places where fusion really fits amazingly well into our energy grid and all that it has to offer, both as a science and as an energy technology. But if you've been following fusion at all, you've probably heard at some point, it's 10 years away and it always will be. So this is kind of a joke within the industry, referring to the fact that research on fusion has been happening for decades and decades and decades, and it always feels like it's just around the corner. But now, I think for the first time, we're starting to see some really credible reasons to believe that it really is starting to be 10 years away, and we really are close to commercializing fusion and making it a viable power source on the global energy grid. So the first reason that you should consider that, I think we've lost the screen. Give me 1 sec. I'll share that back again. Actually, while I'm here, sorry, I'm just going to reshare my screen. It dropped, but I'm seeing that there's a few questions in the chat. I guess they weren't coming up on my other view. So Douglas, thank you for highlighting the 5 approaches. Among them, do you guys see field reverse configuration fusion as potentially better positioned than renewables alone to replace natural gas for always-on AI data centers, given its promise of gas-like dispatchability without carbon emissions and intermittency? Right. So, Durga, thank you so much for bringing up this question. It's actually a really important point that goes along with capacity factor. It's something that we don't have enough time to get into today as a full dedicated topic, but one of the other drivers of the commercial viability of energy sources is how much it can be ramped or adjusted to match the needs of consumers in that market. And what you're talking about here is a really critical factor. As Sergey is saying in the chat, we don't actually have these plants operating as commercial energy production just yet. But the reason that we might invest in or continue to pursue field reverse configuration is exactly what you're saying. It's an important part of that mix of different solutions that are coming forward in the fusion industry because it can be more adapted to the needs of the market more efficiently. And that makes it a great carbon-free replacement for other fossil fuel-based approaches. The other question, don't most fusion reactors need to be replaced in much shorter timelines due to neutron damage? So Krishna, another excellent question. One of the biggest areas of science research happening right now around fusion is actually material science, because to your point, current tests on current materials are not actually justifying a claim of a 40-year lifespan or a 50-year lifespan. But this is a critical hurdle that needs to be reached for this to be a viable industry. And companies will not go forward with building out designs until materials have succeeded in reaching that type of resilience that we need in order to have a longevity in spite of that neutron damage. We are seeing good, credible reason through the continuation of that scientific progress, though, that does suggest it's realistic to believe we will have those type of materials in line with the needs of the industry. I think I've hit everything. Thank you. How do we measure the rate of academic breakthrough in material sciences? So this is a great question as well, Krishna. We don't have the graph here in the presentation, but if you remember the curves that Sergey showed earlier, showing our general progress towards Q, this is generally the way that scientific progress is plotted. You identify a key target metric, and then you can actually plot the progress of what people are achieving against that metric. We have one other question in the chat. What about reactor construction? It's still a massive undertaking too. Fission oftentimes is stuck because of timeline and cost. Why would that be different for fusion? So, perfect question to bring us back in here. I'm going to actually jump back a few slides. So there's 2 reasons. So first of all, we talked about, here we go. We talked about the fuel safety, the safety to life, and also the and also the lifespan and also the end of life safety of fusion materials. And because of all of those being so much safer than fission, it doesn't actually require the same level of regulatory burden that's placed on fission because of how damaging a poorly managed waste system could be for that environment, and because, like we talked about here, there is no capacity for the type of failure that we actually most heavily safeguard against in a fission reactor, which is that growing chain reaction and supercritical event. So hopefully that gives you an answer to the question, but essentially that's what we're talking about here with the regulatory estimates based on fission. And that's why that top end of this graph is so high, and why it's critical, like we'll talk about later, that we regulate fusion separately. So jumping back in here, first of all, we had talked about the fact that, finally it might be 10 years away. So why? Well, the first thing that we're seeing is governments are creating not just forecasts, but actual structural plans for how to incentivize and build systems and industries within their countries to support the commercialization of fusion. And many are making predictions and plans around those predictions to ensure that they actually come true around a commercialization in a 2045 timeline. Next, when we talk to players in the industry about when fusion will reach the grid or when it'll be economically competitive, we're seeing numbers between 2030 and 2040, which is rapidly approaching. One thing that you should have a little bit more color around, though, is that there's been a lot of news coming out about contracts being signed with fusion suppliers. You may have heard of Helion, Microsoft, Commonwealth and ENI, or Commonwealth and Google. And while we do not have the details of those contracts, what we do know is that these are commitments. These are commitments to purchase power if the supplier, Helion, Commonwealth, Helical, TAE, is able to produce energy at a given cost. So typically when this type of agreement is made, again, we don't have the details of these contracts. Typically, these are agreements where if a cost level can be achieved, then a purchase commitment will be triggered. And but because energy is such a commodity, if those prices are reached, it's likely there will be a large market for them anyways. So while this is a good signal, it's not it's not our most credible indicator that we believe in when we estimate that it really is going to be 10 years away. It's not because of these so much as the other factors and the credible plans that governments are making towards realizing a commercial fusion industry. So what does that look like in detail? I'm going to dive into one of those specific plans, which is the American Department of Energy plan, where, as you can see, they're actually planning out both private and public tracks to accelerate the development of these plants over even what they're calling the long term as 5 to 10 years, and then the subsequent support of what are called FOAK, or first of a kind, basically the first plant within one reactor design, up to NOAK, or nth of a kind, when we have many deployed on grid, and how we support that journey. So because they're planning for this, there are incentive programs, research investment, and investment in companies, as well as milestone programs that structurally will guide us towards that timeline. And it's because of this that we're starting to see this really dramatic ramp in terms of the number of companies operating in the fusion industry today. Those companies serve many different customers and many different end products, though. So let's talk about a few of the biggest areas. So we have electricity generation and off-grid energy. This is kind of the most traditional topic you might think of. But another major one is industrial heat. So we want to be able to conduct processes like steel smelting that require enormous amounts of heat that electricity is not typically well suited to addressing as compared to coal or natural gas. But fusion allows us to produce such an enormous amount of power in one place that we can actually support those use cases in a way that other electrical generation just can't. The other part is because we're splitting and combining and adapting atoms and releasing different atomic isotopes, there's an enormous opportunity in the medical field to produce specialized isotopes that are needed for things like cancer treatments and research and other applications. So these are probably the three biggest potential markets for fusion. But as you look at them, this is the other half of understanding the economic viability of fusion as an energy source. And that's that while we do have the LCOE defining the potential cost to create fusion energy, we also have these different markets which value the end product of fusion differently. So what somebody might pay for heat may be different than what somebody might pay for electricity. And because of that, we're able to potentially, even if fusion is not at the absolute bottom of that cost range, still find viable markets where it's extremely valuable to decarbonizing the grid. Now, we've talked a lot about different different types of design, different machines, et cetera. But there's so much more that goes into the industry than just the fusion machines themselves. And this is where we get into the larger fusion industry. There's over 400 companies participating in this space, and they go all the way from supporting technology developers, funding of different kinds, government and investment and private investment, research organizations, the fusion machine developers that we've been talking about themselves, and then this critical sector that doesn't get talked about enough of non-governmental organizations. So let's walk through those and better understand where each of these different types of player comes in. First of all, we have the larger supply chain. So what I just showed you on the last slide is the core kind of, you could imagine as the full-time industry, the dedicated businesses that are focused on fusion. But when we look at the larger supply chain that supports fusion, it contains 400 members or players in that chain alone. Now, some of those players are actually designing full components, parts that are pre-built and integrated into the machine as it's built into a power plant. Other ones are building, smaller components with less commitment. You can imagine there's lots of bolts, lots of raw metal, things like oil that are being used as lubricators, et cetera, within these entire plants. And because of that, there are lots of players in the supply chain that are contributing very small components or elements. And then you can look all the way across as you go deeper into the supply chain, all the way back to mining, steel smelting, et cetera, that goes into creating the materials that are required for fusion to happen. And then lastly, there's a whole sector of services. This is software and engineering services, as well as AI tools that do things like create digital twins or help with the modeling and even operation of these fusion plants. But what's really critical as we go into these different players is understanding how they look at fusion really differently than the way that a scientist might look at fusion. So while a scientist is really looking at that Q scientific metric, or potentially things like the individual components, temperature, or material resilience, et cetera, these players in the supply chain, many of them are new and many of them are dependent on what few fusion companies there are for their entire business strategy. So they're looking at things like valuation, runway, cash flow, unit cost, and material cost. Second, there are a huge number of different investors across the industry that are providing the funds that support the development of fusion. These are both government and private investors, and they really drive their decision-making on things like ROI. So what is the payback that I'll gain from investing in this approach? Or from the government side, how many new businesses are being formed in the wake of the program that we're running? How many green megawatts are being generated because of the program that we're running to support fusion? The next group that we talked about is research organizations. So there are many different organizations around the world, including a few examples here, but they have contributed enormously to the ways that we have achieved the progress that we have within fusion. Historically, though, they used to focus much more on designing the entire fusion machine. So you can see approaches like JET from Eurofusion, work from the Plasma Science and Fusion Center here at MIT, developing magnets, Lawrence Livermore National Laboratory generating the first Q greater than 1 scientific reaction with their inertial confinement system. But increasingly over time, as those systems and the entire fusion machine become larger and orders of magnitude more expensive, that is moving increasingly out to the private sector. And what labs are focusing on is things like material science that we were talking about earlier. So this is probably where the metrics will feel most familiar, but these types of organizations are looking at things like gain factor, milestone completion, technologist readiness level progression, and other factors related to the progress of their core science. But even now, as they continue to specialize more in things that are within the investment range of a school or a research entity, almost all major players in fusion, even in the private sector of fusion, are heavily dependent on these players for their designs and for their development. You can see on the left, most of the names that are sort of household names now that you might be familiar with are direct spinouts of programs run at these major universities and research institutes. And even those that are not coming directly out of those institutes have been developed in very close collaboration. Critically, though, the alignment, this is a space that allows different countries to be more or less involved, even when their investment space may not be directly aligned to supporting the type of investment needed for fusion. And what's really exciting here is that we can see out of all the test and experimental and research reactors that have been built around the world, Japan is actually the leading player. Even though, like we saw in the map earlier, Japan is not a major player in the current commercialization of fusion. So this is really exciting. We can see that over 22 different research reactors have been developed in Japan, and other countries as well have gotten to play at levels that may be beyond what their financial structure is set up to support commercially. So we've talked about this a little bit already, but it's important to come back now as we talk about kind of the core, the heart of the fusion industry, these fusion machine developers, that they exist on a spectrum. I know we've talked about a few examples. We've dove in a little deeper to look at this design or that particular design, but all of these range across a wide variety of approaches, many of which are blended with each other. So you can see that there's, magneto-inertial, we talked about Helion, general fusion, but also magnetic confinement. And then zap energy is, somewhere closer to the magneto-inertial side of that. As we go further around the spectrum, we look at inertial confinement, and then all the way to hybrid magnetic electrostatic, and some very interesting, unique designs that don't even perfectly fit within this array. So I think what's really critical to understand here is that when we think about challenges and solutions to critical evolution points in fusion, that there's no one size fits all answer that's going to address the entire industry. But there's a critical opportunity and a need for us to increase the connectivity and relationships across the industry so that more of what's developed and more of what progresses can serve as many players and as many designs as possible. As you can see, these developers are distributed around the world. I know we went into this earlier, but now that you've seen where those different players are, it's useful to kind of refresh what that distribution is, with a big focus in the US and in China, and a smaller number of players also in Europe. Now, like I mentioned, that connectivity and that sharing of insights, but also larger social reach is a really critical factor in the progression of the fusion industry. And this is where government and non-government organizations come in. So this is where we look at players like Fusion Industry Association, Fusion Energy Base, distributing information and sharing coordination across the industry, helping these different players of these diverse methods stay up to date on what innovation is happening across multiple different research streams that might help them advance their path. Next, we have energy advocates, which are really pushing for more inclusion of fusion in the future energy grid, and who really help us with a a challenge that we'll talk about later, which is public perception around fusion. Now, when we looked at that slide on those slides on why fusion is different than fission and where it might be safer, cleaner, et cetera, that may have been the first time many of you were aware that there are such dramatic differences between fusion and fission. And when we look at the larger group in society, there are tons of misconceptions or just lack of understanding what fusion is and what fusion offers. So these players are critical to gaining the public support that we need to drive a global fusion industry. Lastly, this overlaps a little bit with our research organizations, but science and technology platforms are critical for creating the environment where this research and development can happen. When we look at these players, again, it's a whole new set of key metrics that they're evaluating themselves on. We're looking at research, publications, legislation passed, grant portfolio performance. And as you might imagine, these different metrics require a completely different skill set, a set of skills, and a set of experts to support these organizations. So the last thing we're going to look at, and then we'll pause and do some more questions, is the regulatory policy. Now, I've hinted forward at this multiple times, but it's because it's so critical to the way that we're able to commercialize fusion. So far, only 2 countries have regulated fusion independently from fission. Right now, there's no dedicated fusion policy, but at least these countries are regulating fusion under the regulation designed for particle accelerators, which have the same low risks associated with fusion. But other major players, even though they're working along the path to treating fusion in a dedicated way, they currently are treating it like fission. And as we showed in that levelized cost of energy graph, it is critical that these countries and others continue to make that progress along moving fusion into either its own category or a more appropriately allocated category of regulation that doesn't create undue burden and undue cost on it as an energy source. So that was